Assalamualaikum and good morning. So today we are going to continue on the energy balance on the non-reactive processes. Okay, now let's start. If you are referring back from our last study or previous study, we are learning on the mechanical energy balance, right? So today we are going to focusing more on the chemical processes where the changes of enthalpy and the changes of internal energy plays much more important roles compared to the kinetics energy and the potentials energy. This is where the system having no moving parts in the system, or there's no energy is transferred by the electricity, or even the system is stationary. So we can assume that our shaft work to be zero, and we can even neglect our potentials energy and the kinetics energy as it's going to be zero. So then the energy balance equation would become only between the heat and the internal change of internal energy for the closed system. As for the open system, is between the rate of heat and also the rate of enthalpy. So here we are going to learn how how to calculate, or we're going to learn the procedure to evaluate the change of internal energy and also the change of enthalpy, as when we can't refer any tables for all the processes species. When I say we can't easily refer to any tables because, okay, as you can see in this example, okay, there's one example here when you need to calculate the enthalpy change for the solid phenols at 25 degrees Celsius and at 1 atm. It's going to be converted also to phenol vapor at 300 degrees Celsius and 3 atm. So when you see these questions, you can see that there's too many things is happening actually. Okay, first one, there's no table for the phenols. For this substance, because what we have is a steam tables, right? We are mostly referred to that steam tables for water H2O. So here is first it is a phenols. You don't have phenols tables. Second is where the phase changes from solid directly to the vapor. Okay, so you don't know the situation at this when it's solid or in the liquid form or even the vapor. So the second is that third is there's a changes not only on temperature but also pressure. Okay, so you can see there's four different things that you don't know. One is the phenols, don't have the tables to refer to. Second is the change of phase of the substance from solid to vapor, directly to vapor. So you don't know what happenings in the between of the changes of the phase, and not only one change of the properties, is there's a changes with the temperature and the pressure. So what we are going to do, so this is where we need to construct the hypothetical path. Okay, let's go to next slide. As I said before, we can't easily calculate this internal energy and the enthalpy by just having a simple equations, because too many things is happening in one question. Okay, so we need to have a certain path or certain way procedure to calculate the change of enthalpy and the change of internal energy. This is going to be associated with a certain process, such as first, when there's a changes in the pressure at the constant temperature and at the state of aggregations. And then second is when there's a change in the temperature at the constant pressure and the state of aggregations. Third is there's a changes in the phase at constant temperature and pressure. And lastly will be the mixing. So we are having a mixing of two liquids or dissolving of a gas or a solid in a liquid at a constant temperature and pressure. So we need to have step by step. But you need to remember that we can only change one thing at a time. So leaving the rest going to be constant. So you need to having this procedure or certain process, okay, to be included. So before we start on how to construct or how to do the procedure of the hypothetical process path, you need to know that the specific enthalpy and specific internal energy is or are the state properties. So these properties are dependent on the state of the species, which is primarily on its temperature or the state of the aggregation. The state of aggregation is can either be its phase. It can either be is it in liquid or is it solid or gas. It also depend on its pressure. As for the mixture of some species, it depends on its mole fractions in the mixture. So the state properties does not depend on how the species reach its state. Okay. So consequently, this species path from one state to another, both of change of internal energy and the change of enthalpy for the process are independent of the path taken from the first state to the second one. A hypothetical process path is assumed between the initials and the final state for the purpose of calculating a state property changes. So here I'm having a simple examples. So we are having a PV diagram, a pressure volume diagram, where the process is from point 1 to point 2. So let's assume our point 1 is to be our initial states and point 2 is our final states. So from point 1 to point 2, we are going to have changes in a pressure and volume at the same time. So what we are going to do if we can't solve it at the same time, so we need to have a hypothetical process path. So this is where you are going to refer to the blue path and the red path. So you may having a two hypothetical process path. So it can be you want to solve the pressure first, or you want to solve the volume first. So as long you need to change one thing at a time, leaving the rest at constant. So for example, in blue path, you are having a P change at constant volume first, and then you having a volume change at constant P for next changes. Okay, for while the red path is going to be the vice versa, where you are having where you construct a path having a V change at constant pressure first, and then from the state 1B to state 2, you are having a P changes at the constant V. So it can be either way, but you need to know that hypothetical process path can be having many steps. Okay. The procedure to have the hypothetical process path, where you need to construct the series of hypothetical process path from the initial state to the final steps. So you can't just skip or you want to start from at the middles. So it need to be from initial to finals, and it's going to have consist of series of steps. It's not going to have only one step. Okay, so this you can refer on our previous slides that we have been discussed. And then lastly, then you can calculate your change of enthalpy for each step, and then you can sum all up to get the change of enthalpy for the whole process. So here in the figures below, it shows you examples there where you want to find change of enthalpy for the solid phenols at 25 degrees Celsius and at 1 atm. So this is our initial state, and then it's converted to vapor at 300 degrees Celsius and at 3 atm. This is going to be our final state. So you can see that there's a changes, right? Before I said that they're having a changes not only in phase solid to vapor, but it also they're having a change in temperature, they're having a change in pressure, and also this is a phenols, so you can't easily get it from a tables, or you can't easily determine it directly from the enthalpy table. So in this figure, in the red box shows you the real process or the true path where you want from point 1 to point 2, from the state 1 to state 2, or from initial to the finals. So in the while for the blue box, this shows you step by step. I mean, this is showing you the hypothetical process path that you're going to have. Okay, here you're going to have 6 change of enthalpy, because you're going to have 6 steps. Okay, we're going to discuss later in depth. Here we bring back to our example where we need to calculate the change of enthalpy for a process in which the solid phenols at 25 degrees Celsius and 1 atm to the vapor at 300 degrees Celsius and 3 atm. So to calculate this change of enthalpy, you can't just easily get by H2 minus H1. You can't get it. Okay, you can't get it directly because there's no tables is given in the textbook. So we need to develop the hypothetical process path that going to consist several steps. So okay, first by checking the table B1, because I'm referring the Felder's book, so you can go there, the Felder's Elementary Principles of Chemical Process book. So it shows you that the phenols at pressure of 1 atm. So mostly on the books they're going to give you a standard value. So this they give you the phenols at pressure of 1 atm. So what is the melting point and what is the boiling point? Here the melting point is 42.5 degrees Celsius and the boiling point is 181.4 degrees Celsius. By giving you the melting point, you can also assume your phase, right? Okay. So here shows you this is our phase 1, right? Given the question from phase 1, this is our initials, and then this is our final state. Okay, so for the change of enthalpy at for each steps, there's going to have 6 steps. So this is going to be our hypothetical process path. Okay, first is when we assume we need, you need to remember that we need to change one thing at a time, leaving that the rest at constant. I keep saying this because you need to remember this. Okay, by referring that the specified change in the state, there's 4 types state, right? I give you from the last slide. There's 4 types of specified change in the state, whereas there's a change in P at constant T and phase, and there's a change of T at constant P and phase, and then there's a change of phase at constant pressure and temperature, and also there's a mix of liquid species. So that's where you're going to consider all this change in state. Okay, first is here where in 1 there's only going to change in temperature. So and then it has constant pressure and phase. So you need to have only one thing change at a time to calculate for each step, each stage of change of enthalpy. So here they change 25 degrees Celsius until 42.5 because it will reach their melting point, because this is from solid to liquid. So there's going first is having a change of temperature. Next, they're going to have a change in phase, where having a solid to liquid, but at others is going to have a constant. Make sure others going to have a constant, to be constant. Okay, remember, we need to change one thing at a time. Okay, this is going to be heat up to melting point, and then this is going to be changes of phase, solid to liquid at constant temperature and pressure. So you're going to have a change of enthalpy at this stage, and then at this stage where they're having you a change of temperature, where you need to achieve boiling points at 181. So this is point 3. So from the point 3 to this point, so you're going to have a change of enthalpy at point 4, at step 4, where we're having a change of phase, because when you reach 181, it start to vaporize, really, right? So there's going to having a phase change, where from liquid to vapor, so at a constant pressure and temperature. Okay, make sure each step to have only one change. So that's why you're going to have this 6 change of enthalpy for each steps. So lastly, you're going to have change of pressure, because from 1 atm they're going to change to 3 atm. Okay, you need to do step by step. So this is what the hypothetical process path. So to get the sum of the change of enthalpy from the initial to finals, you need to sum up for each step of their enthalpy. So next is the calculation for the energy balance. So you know that most of the problems of this energy balance given you some values of the process variables, right? For such as feed, what is your product stream, temperature, pressure, amount of flow rates, or even the components of the mole fractions. So lastly, you need to calculate these certain values, such as when you need to calculate the heat that going to be transferred to or from the process system. So you will require or writing and solving an energy balance. So you need to have a procedure to follow for the energy balance calculations. So later on, I'll discuss on for one example later. So here, I'm just going to list out step by step, one by one, what you need to follow, okay? First of all, where you need to perform all the required material balance calculations, okay? As I said before, even in the mechanical energy balance, how you to solve mechanical energy balance. So first of all, you need to perform all the required materials energy balance. Try to solve it first, okay? Second, you need to write the appropriate form of energy balance. It can either be closed or open system. And then delete any terms that are either be zero or negligible for the given process system. So in this step 2, you need to know this question given you, is it going to be open or closed system? So which of the energy given is going to be zero? Is it going to be adiabatic, or is it going to be insulated? Is it going to be isothermal, for example? Is it the kinetics energy going to be zero? So this is where the step that you need to know what system you use and delete any of the terms that's going to be zero or negligible. And then third, you need to choose a reference state for like a phase, a temperature, and pressure for each species involved in the process. So if the values of internal energy and your enthalpy will be looked up in the tables. For example, the steam tables for water. So you need to choose your reference state used to generate the tables, or other else you choose one or of the inlet and outlet states of the reference state for the species. Okay, and then the fourth, you need to construct a tables with columns for initials and the finals amount for the specific uh, internal energy as for closed system, and for the specific enthalpy as for your open system. Okay, so your U internal energy initials and your enthalpy initials should be specified relatively to the chosen reference state. The next step is where we need to calculate all the required values of the enthalpy and the internal energy, and insert the values in the appropriate place in the tables. Okay, so this is where we focus on this chapter 8, where we need to find these values, this internal energy and your enthalpy. And then for the 6 steps, where you then calculate the total change of enthalpy and the total change of internal energy for the system. So given here is the uh, equation for the closed system and open system for the enthalpy and the internal energy, where the outlets minus to the inlet of the internal energy and the enthalpy. And then next, you need to calculate any works or any kinetic energy and potential energy terms that have not dropped out from the energy balance. So if they're still giving you the data, so please include it back. Okay, even though I said that this is only going to be focused on to find the internal energy, but if in the question given you these details of the works and kinetic energy and potential energy, do calculate it, okay, at this step. And then at 8, where we need to solve the last one, we need to solve the energy balance for the unknown variables. The question asking you what is the variable value. Okay, so you make sure you know the main equation for the open system and the closed system. Okay, so you need to remember you have all 8 steps to do. So here is our first example, the energy balance on a condenser. The acetone is partially condensed out of the gas stream, so containing 66.9 mole percent acetone vapor and the balance nitrogen. So the process specification and the material balance calculation lead to the flow chart shown below. So the process is going to be operate at steady state. So you need to calculate the required, okay, the required cooling rate. So you need to be required means it's going to have, you're going to have your Q dot in what? Required cooling rate going to be in negative because it's a cooling. So your answer need to have in kilowatt, joule per second. So for the solutions for these examples, first, as you can remember, the list down or the procedure of the energy balance calculation. First of all, you need to perform required material balance calculations. So here in this example, you don't need to, because it already gave you the amount of substance mole per seconds for the inlet and your outlet. So you already know it. So as starting is the basis is starting at 100 mole per second for the mixed gas of acetone and the nitrogen, and your outlet's going to have a 36.45 mole per second for the mixed gas of acetone and nitrogen, and also for the 63.55 mole per second is your outlet for the acetone in liquid form. Okay, so you're going to have two outlets and one inlet. So first, you're already done. So second, the energy balance. Even in the equations, it's asking you to calculate the cooling rate. It means need to have in a unit in joule per seconds. So it is a steady state system. So this is going to involve you in an open system. So what is the open system equation? So you need to remember this equation, right? It is Q rate minus the shaft work rate equal to change of enthalpy rate plus the kinetics energy rate plus the change of potential energy. So as you can refer back on this system, it doesn't state any moving parts. So or there's no energy is transferred by the electricity or even in the or radiations. So you can assume that our shaft work going to be 0. So you need to cancel out because you need to simplify and cancel any terms that going to be 0 or negligible. So it also occurs for the our kinetics energy and the potential energy, because there's no any change of the distance, or even they don't say any velocity, so we can assume that it is negligible. So your kinetics energy, your potential energy is going to be assumed as 0. So your energy balance going to have a Q rate equal to change of enthalpy rate. Okay, so you're going to have your this final energy balance that you're going to refer to. So third, you need to choose your reference states for the acetone and nitrogen, because in this equation you are going to have you are going to relate on the acetone and the nitrogens. So where that you can refer to this data. So given that your nitrogen is any nitrogen is at gas state, and it is at 25 degrees Celsius and 1 atm. So then this going to be your reference state. So you're referring at the table B8. As for the acetone, the liquid at 20 degrees Celsius and 5 atm. So there's no enthalpy data that be given. So you can't refer to any tables. So at step 4, you need to construct an inlet and outlet enthalpy tables. So what you need to have in this inlet and outlet tables, so you need to list down all these flow rates. Here, the example involved in mole rates, right? In mole per second. So you need to fill in for the mole rate and also for the specific enthalpies for given substance. So here, the substance that involved in these examples are, as we having a mixtures of gas, right, of acetone and and nitrogens, the ideal gas, so in vapor form. So here we have these two mixture gas, and also you're going to have two outlets, right? So one of the outlets to have the acetone in the liquid form. So you need to list down all your substance and all the what is going to have your for the inlet and your outlets. So next you need to fill in the form to fill in the tables the value that you're going to have. So you know that the acetone in vapor form, the inlet is going to have around 66.9 mole per 66.9 mole. So how you get the 66.9? So if you're referring back the flow chart, right? The acetone vapor per mole is going to have a 0.669. So the total rate is going to have 100 mole per second. So that's why you are going to have a 66.9 here, this value. Okay, so just fill in. So this is going to apply to all these inlet and outlet for this mole rate. As for the nitrogen, it's 33.1. So for the inlets, there's no acetone in liquid form. So you just put a dash, means there's nothing, or just cancel out, or you don't need to put anything. So for others, just put all the data given. So you know how to calculate this. This is going to have the moles of your acetone vapors times to the total moles outlets for the first outlet. 0.092 times to the 36.4 mole per seconds. So here you're going to have a 63.55, the overalls of this mole rate, and then this is 33.1. So for the each inlet, for the each mole rate, you're going to have a specific heat, specific enthalpy point for each steps. So here just recorded as a enthalpy 1, enthalpy 2 for the outlets, and this it is enthalpy 3 for these nitrogens for the inlet, and also the outlet for the nitrogen gas. We noted it as a enthalpy at 0.4. So here there's a note following that you can refer to, that you know, right? There's a nitrogen that has only one state. Okay, means one state means it's only in a gas form, gas phase. And acetone has one inlet state but have a two outlet state. When the two outlet state means it's going to have in a liquid and in vapor form, but in inlet it's only going to refer on a vapor. As why this we assume it to be 0? Because we made the reference state for the acetone. Okay, we take the acetone at liquid form at 20 degrees Celsius and at 5 atm as reference state. So this we state it to be, we're going to have our specific enthalpy to be 0, because this is our reference state. So that's why it's going to have 0 value. At step 5, we need to calculate all the unknown specific enthalpies in this step, where we need to find all the specific enthalpies that have been listed out in the tables at step 4, where we need to find the enthalpy 1, enthalpy 2, enthalpy 3, and enthalpy 4. So where we need to calculate. So there's a where we need to calculate the change of enthalpy and change of specific enthalpy for a specified change in the state. So there's 3 steps where we going to refer to as one, where there's a change in a pressure at constant temperature and phase. So the equation is going to be the change of specific enthalpy equal to specific volume times to the change of pressure. So why we have this equation? Because if we are related to the ideal gas, yes, the change of enthalpy, change of specific enthalpy, going to be 0 because due to the constant temperature, isothermal. But if for the solid and the liquids, so we back to the change of specific enthalpy is equal to change of the specific internal energy plus to the change of PV. Okay, because we are referring to the solid and liquid. So as state that the isothermals, yes, your change of internal energy going to be 0, and there's no changes in the specific enthalpies. I mean, there's no changes in a specific volume times to the pressure. So this also being cancelled out to be 0. So the only left is where there's a specific volume times to the change of pressure. So because that we're going to have these equations. So later we go through why we going to adapt this equation, okay, at the specific change in pressure at constant temperature. So second is for the changes in the temperature at a constant pressure. So you still remember, right, we learned about the specific heat capacity at a constant pressure where we need to determine our change of enthalpy. So this is also represent the change of specific enthalpy at when there's a change in the temperature at a constant pressure. So we are applying our the heat capacity. So the third is there's a change in phase at constant of pressure and the temperature. So here we are going to apply the heat of the vaporization and the heat of melting at the normal boiling point and normal melting point respectively. So this data of enthalpy, specific enthalpy, can be obtained from the table B1. Okay, from this book, from the Felder's book. Felder's The Elementary Principles of Chemical Processes. Okay, let's start the process to determine our H1. Okay, you know, right, our reference state for the acetone is, where we set is here, right, the acetone liquid at 20 degrees Celsius and at 5 atm. So we want to find our H, change of H1, specific H1 until we achieve our feed of acetone at vapor phase temperature at 65 degrees Celsius at 1 atm. Okay, so this is our final state. Because we want to do a hypothetical process path, okay, because it's going to have like a change in liquid and also change in the temperature. There's also change in the pressure, so there's many things that happen at once. That's why we need to have our hypothetical process path to determine our total change of H1. Okay, so this is our point 1 to until our final state at point 2. So this is where each steps occurs, as from this A, for the A steps, where we have change in a pressure. Okay, at B step we have a change in temperature, because we need to have only one thing change at the time, and leaving the rest to be constant. Okay, you remember, right? I keep saying this sentence or words. This is where happen the change of the temperature at constant pressure and constant phase. So at step C, from the acetone liquid 56 degrees Celsius 1 atm, and then there's change of V. So here happen to have a change in phase at constant pressure and at constant temperature. So at D step, so we are having our change of temperature at constant pressure and phase. So here is the calculation for our step A. Okay, for step A of the hypothetical process path, we want to determine our change of specific enthalpy 1A, because this is total, right? In the tables at step 4, we need to find our change of enthalpy 1, specific enthalpy 1. So we already calculate our step A for the change of enthalpy 1A. Okay, so we already did this, so you can refer to our previous slides. So at step B and step C, so the changes occurs is there's a change in temperature at constant pressure. So we are going to apply to have a heat capacity at different temperature. So you can refer to this the green box. As for the step C, there's a change of phase, means from the liquid to the vapor. So means there's having a vaporizations, or you can have a boiling temperature. So you can refer to our table B1. So where it occur the vaporizations. Okay. So at temperature boiling point given at the pressure of 1 atm. So this is the change of specific enthalpy. So lastly, you just need to substitute. Substitute all the data that you have been recorded, where you have been referred to the to each tables for certain conditions. So here, the change of the specific enthalpy. The specific enthalpy 1 is equal to the change of specific enthalpy at step A plus the change of specific enthalpy at step B, and then plus the change of specific enthalpy at step C, and then lastly the change of enthalpy at step D. So you just substitute all that what is going to have you been referred to. So at the end, your specific enthalpy that you're going to get is 35 kilojoule per mole. So later you need to use the same manner that you calculate this specific enthalpy of 1 for the other values of the H2, H3 and the H4. Okay, I hope we can do it. Try to be doing a step by step, okay? Make sure you understand later. So you'll be understand later. So later when you finish or you have determined all these H2, H3 and H4, so make sure you insert all these specific enthalpy that you have find into the inlet outlet enthalpy table that have been drawn at step 4. So to make sure you have complete to determine all these specific enthalpies. So next we're going to go to our step 6 where we can calculate our the total change, okay, of the system, the total change of the enthalpy rate. So the enthalpy rate is where the total of at the outlets means time the substance rate times to the specific enthalpy at the outlets minus to the total of the substance rates times to the specific enthalpy at inlet, okay, outlet minus to inlet. At step 7, we need to calculate any non-zero work kinetic energy and potentials energy terms. So when we are referring back on our step 2, we already cancel out any that terms that going to be zero or neglect. So here also we already know that our shaft works there's no need to be calculated because there's no moving part, right? So we also can neglect our kinetics and the potentials energy. So the step 7 can be skipped. So lastly, our step 8 where we need to solve the energy balance for the Q rate. So as we also can refer back our step 2 where we already simplified, we already make it easy for the energy balance, right? The simplified energy balance is the Q rate equal to the change of enthalpy rate. So we already determined our change of enthalpy rate at the step 6. So we just substitute it is equal to negative 2320 kilojoule per second. You can also put it as in kilowatt. So the heat that must be transferred from the condenser at the rate of negative 2320 kilowatt to achieve the required cooling and condensation. On the last examples, you are applying the changes in pressure at a constant temperature to calculate your and specific enthalpy. So here a bit details is it you can assume either can be zero or not. So for the ideal gas, both of the specific internal energy and specific enthalpy are independent of pressure for the ideal gases. Thus, you may generally assume that your change of your specific enthalpy and the change of your specific internal energy can be zero. Okay, thus that it not valid for the gases well below the 0 degree Celsius or well above the 1 atm are involved. So if of your specific internal energy and your specific enthalpy at given Tp, given the temperature and pressure are available, so do not use the above equations. If gases are far from the ideals, or we can say it's a real gas, or it undergo a large of change of pressure, you must use property tables or sophisticated thermodynamics correlations. Okay, and as for the real gas, okay, here I say that if it is real gas, you can't just easily assume is it going to be 0, because you need to evaluate from the enthalpy departure charts or from the equation state or the tabulated data. As for the liquids and solids, okay, yes, your change of your specific internal energy can be assumed to be 0, but your change of your enthalpy is going to be equal to the specific volumes times to the change of your pressure. The next criteria where we need to find or to calculate our change of enthalpy in the terms of hypothetical path, it is where there's the changes in the temperature at a constant pressure. So the sensible heat is the term which is used to define the heat that is actually transferred to the system to raise or to lower the temperature of a substance mixture. So when there's a change in the temperature, there's actually sensible heat which is supplied to the system. So this heat is absorbed by the system and the temperature is actually increased because of this heat supplied. The sensible heat can be calculated from the change of the internal energy or the enthalpy, and this value can be directly used for the understanding how much energy is needed or to be supplied, or the heat need to be supplied to increase the temperature of the system to one point to another. Okay, so we've been learning about the heat capacities before. So to calculate the heat capacity at a constant pressure, we call it Cp to the delta specific enthalpy to the over delta temperature at a constant pressure. So the enthalpy changes at a constant pressure are given by the integrations of this system. So you can determine that the change of the enthalpy, specific enthalpy, is Cp times to the change of the temperature, final minus initials. So to determine for the changes in the internal energy, we can calculate by the heat capacity at a constant volume at difference times to the difference of the temperature. So for the ideal case, the Cv is equal to our heat capacity at constant pressure minus the R, our gas constants. As for the liquids, we can assume that our Cv is nearly same to the heat capacity. The last process that we encounter in the examples where we need to calculate the enthalpy for the hypothetical process path is the phase change operations. Okay, the phase change such as a melting and evaporations are usually accompanied by the large change in the internal energy and enthalpy. So usually we're going to see the latent heat occurs for the problems, as the specific enthalpy change is associated with the transition of a substance from one phase to another at a constant temperature and pressure. So the most common is where we are having a melting and a vaporizations. So for the melting, or we call it also as a heat of fusion, It is a specific enthalpy difference between the solid and liquid. So this is where the phase changes from the solid into liquid forms as this is at the constant at given temperature and pressure. As for the heat of vaporization, it's a specific enthalpy. There we need to specific enthalpy difference between the liquid and vapor. So this for the vaporized is where the changes of the phase from the liquid to vapor forms of a species at the given temperature and pressure.